2.4 One-sided limits. The outline of this video is as follows. We will discuss how the new concept of one-sided limits relates to the two-sided limits we have already explored, establishing a crucial connection with what is called Theorem 6. Next, I will provide the formal epsilon-delta definitions for these one-sided limits, which give us the rigorous mathematical language we need to be precise. With that foundation, we will use these ideas to analyze a very important trigonometric limit, the limit as theta approaches 0 of the fraction sign of theta over theta. We will finish by working through several applications and examples to see how one-sided limits appear in practice, and why they are so useful for understanding function behavior near a specific point. The goal is to build a complete picture, from the core theory to practical problem solving. Sometimes a function approaches different values depending on whether we approach a point from the left or the right, which is why we need one-sided limits. While a standard two-sided limit requires a function to be defined on both sides of a point C, a one-sided limit examines the behavior from just one direction. A right-hand limit describes what happens as x approaches C from values greater than C. Conversely, a left-hand limit describes the behavior as x approaches C from values less than C. For a clear example, consider the function f of x equals the fraction x over the absolute value of x. As x approaches 0 from the right, the function value is always 1. However, as x approaches 0 from the left, the value is always -1. This demonstrates that a function can have two different one-sided limits at the same point. Sometimes a function behaves differently depending on which side we approach a point from, which is why we have the concept of one-sided limits. A right-hand limit describes the value a function f of x approaches as x gets closer to a point C, but only considering x values that are greater than C. We write this notationally as the limit as x approaches C with a plus sign. In contrast, a left-hand limit is the value the function approaches as x gets closer to C, but only from x values that are less than C, which we denote with a minus sign after C. For example, for a function that is 1 for all positive x and -1 for all negative x, the limit as x approaches 0 from the right is 1, while the limit from the left is -1. One-sided limits give us a precise tool to describe a function's behavior on each side of a point independently. Let us explore how one-sided limits work at the boundary of a function's domain, which is a special case where a two-sided limit cannot exist. I will use the function f of x equals the square root of the quantity 4 minus x squared, which graphs as a semicircle on the closed interval from -2 to 2. At the left endpoint, x equals -2. We can only approach from the right side since the function is not defined for any x less than -2. Therefore, the left-hand limit does not exist, but the right-hand limit as x approaches -2 is 0. The same logic applies at the other endpoint, x equals 2. We can only approach from the left, so the left-hand limit is 0, but the right-hand limit is undefined. Because a two-sided limit requires the function to exist on an open interval around the point, a two-sided limit exists at neither endpoint. This shows that at the edge of a domain, we can often find one one-sided limit, but not both. This theorem provides the fundamental connection between the one-sided limits we have been discussing and the overall two-sided limit. It states that for a function f of x to have a two-sided limit L as x approaches a point C, two conditions must be met. Both the left-hand limit and the right-hand limit must exist, and they must be equal to the exact same value. For example, if a function approaches a y value of 5 as we get closer to x equals 2 from the left, it must also approach 5 from the right for the overall limit to be 5. If the left-hand limit and the right-hand limit are different, say one is 5 and the other is -1, then the two-sided limit does not exist. Ultimately, for a limit to exist at a point, the function must be heading toward the same single destination from both directions. Let us apply our understanding of one-sided limits to this graph to see why the two-sided limit fails to exist at two key points. First, at x equals 0, the function is not defined for any values less than 0, so a left-hand limit is impossible. As we approach 0 from the right side, however, the function value clearly approaches 1. Because a limit from the left does not exist, the overall two-sided limit at 0 does not exist. Next, let us look at x equals 1, where we see a jump discontinuity. Approaching 1 from the left, the function's value gets closer to 0. But when approaching from the right, its value gets closer to 1. Since the left-hand limit of 0 and the right-hand limit of 1 are not equal, the two-sided limit does not exist here either. Remember, for a two-sided limit to exist, the function must approach the exact same finite value from both the left and the right. Let us continue our analysis by looking at points where the two-sided limit does exist, which reveals important features of the function. At tx equals 2, notice that as we approach from either the left or the right, the function value gets arbitrarily close to 1. Because the left-hand and right-hand limits are equal, the overall limit as x approaches 2 is 1. However, the function itself is defined with a value of 2 at that point, which we see as the solid dot. This is a classic example of a removable discontinuity. In contrast, at x equals 3, the function is continuous. The limits from both sides are 2, and the function's value f of 3 is also 2. Finally, at the endpoint x equals 4, we can only approach from the left, giving a one-sided limit of 1. Since we cannot approach from the right, the two-sided limit does not exist. This shows that a limit can exist even if the function has a whole or a different value at that exact spot. Now we will make our intuitive idea of one-sided limits mathematically precise using the epsilon delta framework. For a right-hand limit, the definition is nearly identical to the two-sided one we already know. We still require that for any small positive epsilon, the function value f of x stays within epsilon of the limit L. The key difference is the condition on x. Instead of x being in a two-sided interval around x, we now require x to be strictly between xc and c plus delta. This precisely captures the idea of approaching strictly only from the right side. The definition for a left-hand limit is perfectly symmetrical. The only thing that changes is the interval for x, which becomes strictly between c minus delta and s, formalizing the approach from the left. The essential thing to remember is that we are just restricting our x values to an interval on one side of c. Let us now use our formal definition to prove that the limit of the square root of x as x approaches 0 from the right is indeed 0. Our goal is to show that for any given positive epsilon, we can find a corresponding positive delta such that if x is between 0 and delta, then the function's value is within epsilon of the limit. We start with the conclusion we want, which is that the square root of x must be less than epsilon. To see what condition this imposes on x, we can square both sides of that inequality, which tells us that x must be less than epsilon squared. This gives us a clear strategy. We can simply choose our delta to be equal to epsilon squared. By making this choice, we guarantee that if x is in our small interval defined by delta, the square root of x will be in the target interval defined by epsilon, which formally proves the limit is 0. Now I will explore a classic example where a limit fails to exist, which helps solidify our understanding of the definition. Let us consider the function y equals the sine of the quantity 1 over x. As the input x gets closer and closer to 0 from either the positive or negative side, the term inside the sine function, 1 over x, grows infinitely large. Because the sine function is periodic, this causes its output to oscillate endlessly and rapidly between -1 and +1. For instance, no matter how tiny an interval you draw around 0, the function's graph will swing through its entire range of values infinitely many times. Since the function's values do not approach any single, specific number L, the limit as x approaches 0 does not exist. Let us explore a central result in calculus that is essential for finding the derivatives of trigonometric functions. This theorem states that the limit of the fraction sign of theta over theta as the angle theta approaches 0 is equal to 1. Intuitively, this means that for a very small angle, the value of its sine is almost identical to the value of the angle itself. A critical condition for this to be true is that the ascida must be measured in radians. This requirement comes from the proof method, which relies on a geometric formula for the area of a circular sector that is only valid for radian measure. We will soon prove this result by comparing the areas of a triangle and a sector and then applying a tool called the sandwich theorem. The essential thing to remember is that this specific limit is 1, a fact that forms a cornerstone for the calculus of trigonometric functions. To prove that the limit of sine theta over theta is 1 as theta approaches 0 from the right, we will use a clever geometric argument involving areas in a unit circle. For a small positive angle theta, we can see that the area of the small inner triangle OAP is less than the area of the circular sector OAP, which in turn is less than the area of the larger outer triangle OAT. Expressing these areas in terms of theta gives us an inequality. 1/2 sine theta is less than 1/2 theta, which is less than 1/2 tangent theta. After some algebraic steps, including taking reciprocals which reverses the inequalities, we can trap our target expression, sine theta over theta, between cosine theta and the number 1. It is crucial that theta is in radians, as the sector area formula depends on it. This geometric comparison perfectly sets up the squeeze theorem, as our function is caught between two expressions that both approach 1. To find the limit as theta approaches 0 from the left, we can use a clever shortcut based on the function's symmetry. The function f of theta, defined as sine of theta over theta, is what we call an even function. This means that the function's value at negative theta is exactly the same as its value at positive theta. We can see this because sine of negative theta equals negative sine of theta, so when we divide this by negative theta, the two negative signs cancel out, returning the original function. Graphically, an even function is perfectly symmetric about the y-axis, like a mirror image. This symmetry implies that the left-hand limit must be identical to the right-hand limit. Since we already established that the right-hand limit is 1, the left-hand limit must also be 1. Therefore, because both one-sided limits exist and are equal, we can conclude that the overall two-sided limit is 1. Now we will see how our fundamental sine limit can be used as a tool to solve a related problem involving cosine. Our goal is to find the limit of the quantity cosine of h minus 1 all over h as h approaches 0. The key step is to use the half-angle identity, which let us replace cosine of h with 1 minus 2 times the sine squared of the quantity h over 2. After this substitution, the 1's in the numerator cancel out. We can then algebraically rearrange the expression into a product of two separate limits. The first is the negative of the fraction sign of h over 2, divided by h over 2. The second is just the limit of sine of h over 2. We already know the first limit evaluates to 1, and the second limit is simply sine of 0, which is 0. Therefore, the overall limit is the product of negative 1 and 0, which is 0. Now, I will show you how to solve a limit that does not quite fit our standard form by using some clever algebraic manipulation. Our goal is to find the limit of the fraction sign of 2x over 5x as x approaches 0. A problem here is that the argument of the sine function, 2x, does not match the denominator, 5x, so we cannot directly apply our known rule for the limit of sine theta over theta. To solve this, we can multiply the expression by the fraction 2 over 5, divided by 2 over 5. This is a useful trick because it is like multiplying by ones. This rearranges our expression into 2/5 times the fraction sign of 2x over 2x. We can then pull the constant 2/5 out of the limit. By substituting theta for 2x, the inside of the limit now perfectly matches our rule, evaluating to 1. Therefore, the final result is 2/5 times 1, which is 2/5. The main idea is that you can algebraically reshape an expression to fit a limit rule you already know. Let us see how we can combine our limit rules to solve a more complex problem involving trigonometric functions. Our goal is to find the limit as t approaches 0 of the fraction with tangents of t times secant of 2t in the numerator and 3t in the denominator. The first step is to rewrite the expression using fundamental identities, substituting sine of t over cosine of t for tangents and 1 over cosine of 2t for secant. After this substitution, I can algebraically rearrange the expression to isolate factors whose limits are known. This separates the problem into the product of 4 simpler terms: 1/3 times the fraction sine of t over t times 1 over cosine of t, and finally times 1 over cosine of 2t's. Applying the product rule, we can evaluate the limit of each piece. The limit of sine t over t is 1, and as t goes to 0, cosine of t and cosine of 2t both approach 1. Multiplying these values gives us a final answer of 1/3. The main idea is that complicated limits can often be solved by rewriting them as a product of simpler, known limits. Let us summarize the essential ideas of one-sided limits and how they clarify the existence of a standard two-sided limit. We use one-sided limits to analyze a function's behavior as we approach a point exclusively from the left or from the right. The most critical takeaway is that a two-sided limit exists if, and only if, both the left-hand and right-hand limits exist and are exactly equal to each other. While this concept is intuitive, it also has a formal epsilon delta definition tailored for a one-sided interval. We then use this framework to establish a fundamental result. The limit, as theta approaches 0, of the quantity sine of theta over theta equals 1. This special limit, which requires theta to be in radians, becomes a powerful tool for solving more complex, indeterminate forms involving trigonometric functions. Ultimately, checking both one-sided limits is the definitive way to know if a function's limit exists at a point. Let us use these two questions to check our understanding of how one-sided limits work. For the first question, because the left-hand and right-hand limits as x approaches -1 are both equal to 4, we can conclude that the overall limit also exists and is equal to 4. However, this gives us no information about the value of the function mig at -1. Remember, the limit describes the function's behavior near a point, not necessarily at the point, so there could be a hole or a different value there. For the second question, the famous proof involving the limit of sine theta over theta uses a geometric argument. This proof works by comparing the areas of a triangle and a circular sector inside the unit circle, a construction that is valid only in the first quadrant, which corresponds to angles between 0 and pi over 2 radians. These questions reinforce that a limit does not equal a function's value, and that proofs can have important domain restrictions.